So I guess just before we get started, can I see a quick show of hands who has collaborators or coworkers who write on language that's not Python? Okay, so most of us. Okay, so this is not that uncommon of a thing. So yeah, I'm going to talk about a little bit of my experience the past couple of years writing tools. I started in Python, and then I joined a company that's Polyglot, in that we have a lot of workflows that happen in both Python and R. And just some of the issues we've run into in trying to make sure that the same tools are usable across language boundaries. So this is not about Python versus R. I don't think this is like a debate that's worth settling. We certainly won't settle it here. What this is really about is what we call meeting users where they are. For those of you that work on like diverse teams, depending on the fields that your coworkers and collaborators come from, people are trained in different tools and different languages. So R is very popular, for example, at Civis among the people who come from the social sciences, while Python is more popular with some people who come from the physical sciences. So just respecting people's training and comfort is pretty important to tool building. And then also like the availability of key packages. This is probably the number one reason we have to work in two languages, or at least two languages. NLTK is one example, is a NLP library written in Python. Glimnet is one for solving regularized regression in R, and we happen to use both of these in a single workflow, which requires us using two languages to solve a problem. There's also trade-offs. So different languages optimize for different things. Python is definitely a general purpose language. R is very optimized for statistics and manipulation of tabular data, and Go is another example. It's a great fit for network services. So people who use your tools definitely use them for, people who use your tools in different languages choose those languages for different reasons, and respecting that is important if at all possible. So there's a few examples of popular tools that have decided to make bindings for multiple languages. Stan is a Bayesian modeling tool, for example, XGBoost, Spark, TensorFlow, a time series database called TrailDB, and then H2O. So how do they do this? There are two pretty typical ways. One is writing native or compiled extensions in C or C++. This is obviously very fast. Most languages speak C. Python and R, in fact, actually written in C. So it makes wrapping code written in C pretty easy. Cons, it's difficult. C is not an easy language to develop in. It's error prone. Often takes more code to do the same thing because it's a lower level language compared to Python. Examples of tools that have taken this route are Stan and XGBoost. Alternatively, and maybe this is a little bit easier route, is exposing an API over REST, HTTP or IPC. So think like a JSON API as an example. This is, every language that people actually use talks to the internet, which is very helpful. So it makes these types of things very easy to wire up in the host language. The problem is the cost of communication is extremely high. You end up copying data or serializing things rather than sharing memory or sharing pointers. So Spark and H2O definitely went this route. Both are written in, actually both target the JVM, but have very nice Python and R APIs that actually communicate over a RPC type mechanism. So since we don't have a lot of time today, we're going to focus on the native compiled extensions, specifically C. So I went looking around on the internet for somebody that agreed with me. It turns out it's pretty easy to find. C++ is a difficult place to start. I find that C is a little bit easier to start with these things. C++ is kind of like the English language. It has pretty much everything everybody wants. C is a little more constrained. The language itself is simpler, although there's a lot of edge cases and boundaries and little tidbits that you have to know to be successful. So why C? Obviously, as I said, Python and R both speak C, so it makes it, wrapping a C API or a C library, anything that is written in C in Python and R is a pretty trivial task, although there's a decent amount of boilerplate code to do this. A side effect is that it's very fast because it's C. It's mostly portable, although not entirely, but if people are using Linux and Mac, it's pretty much a win. Windows is a little bit more difficult to target. And then the language itself is relatively simple. So again, continue on the Why C course. C has gotten a lot better since I learned it as a lowly undergrad. The tooling has actually come a long way. There's various sanitizers now that they actually won't catch everything, but they make it much easier to identify common mistakes in memory allocation and initialization. There's even an undefined behavior sanitizer now that will very loudly tell you when you do things that are not actually defined in the C or the C++ specification. There's also leak sanitizers, thread sanitizers. There's a whole list of these types of things. And the error messages and diagnostics that come from Clang and GCC are now much more helpful. Not quite as nice as Python, but they've come a long way in the past decade or so. So alternatively, if C isn't a thing that you want to implement a tool in, keep in mind this Hourglass interface, and the idea here is that you have the host language, which is the way your users will interact with your tool. So this could be Python, R, Julia, Ruby. Take your pick among the higher level languages. In the middle, you have the API that's actually exposed, and this can be C99, C89, some less current version of the C standard, again, because everything speaks C. And then at the bottom is the implementation language. This can be pretty much anything that is capable of exposing a C89, C99 API. So that's obviously C itself, Go, C++, Rust, a number of others. And this idea is actually credit to a presentation called Hourglass Interfaces for C++ APIs by Stéphanos Dutoit, which is, I think, probably findable on YouTube. This was at C++Con a few years ago. So we'll work through a code example, and apologies if this is not readable on the screen there. One of my coworkers said I couldn't do CART, which is a machine learning algorithm. I had to start simple because I didn't want to have to explain machine learning too in a talk on writing cross-language tools. So we are going to implement the summation function in C. But the word sum is taken in both Python and R and many other places, so I decided to call it tally. So when setting out to develop cross-language tools, it's best to start in a higher level language that you're comfortable working in, like Python. So not only is it quicker to develop, but you get the algorithmic issues out of the way first before you start messing around with static typing and memory allocation and all those types of issues. It also gives you a standard to compare your lower level implementation. So we always smoke test things, and pretty much what it's supposed to do. And then this is what the C implementation looks like. So it looks a lot like the Python one, not all that different. There's some noise related to the typing of the variables. One other issue in C that's you don't run into in Python is that arrays do not know how long they are, very inconveniently. You need to keep track of this as the developer. So in doing any type of array operations in C, we obviously need to track the shape. And in this case, we're assuming it's a one-dimensional array, so we're just keeping track of the length. So how do we have a C function, how do we access this in Python? There are at least 4 options, probably a number of others. Cython is pretty common. CFFI and C types are similar but take different routes. But we're going to talk about using the Python C API directly. Because it's using Cython to generate C code that you then call in R is very, very challenging. And turns out to not be worth the time, or at least we haven't found it. It's much easier to just bite the bullet and run through the C boilerplate. So this is what a Python module defined in C looks like. At the top, we have our tally function, or a wrapper for our tally function, method table, and then some module metadata. And then at the very bottom is an initialization function that's called when the Python interpreter actually loads the module. So we'll go through these pieces in turn. First is this tally function, or the Python wrapper for the tally function. A lot of boilerplate. Starts at the very top. We get just a pointer to a Python object when the function is called, and here we're unpacking it, telling the Python runtime that we want a object, so a raw object, and then using the buffer interface, we then deconstruct this and again tell the interpreter that we want a contiguous chunk of memory, and then we go and we also double check that what the user passed was an array of doubles or an array of floating point numbers rather than just some arbitrary Python object, and then we return an appropriate error if that's not the case, and then also release the buffer that we allocated through the Python API. And then here is where we actually call our tally function, passing a pointer that we got from the buffer API and also the length of the array, saving that to a temporary variable, and then we pass that back to the caller and release the buffer. So not all that difficult. A lot of bookkeeping stuff that we don't that Python just takes care of automatically for us, but it's not too bad. It's a lot of reading and referring to the API docs, but wrapping C functions is nothing to be too terrified of. And then this is the method table and the module metadata. Nothing too awful, too complex. And then the init function. Getting this into R is pretty much exactly the same exercise. The names change, but the overall format is the same. So everything in R is an S expression. R also makes it a little bit easier. We don't have to deal with the buffer API because there are essentially no scalars in R, which makes things a little bit easier. We again have a methods table and then a registration routine that gets called when the R interpreter loads the shared object that we're compiling here. So this is what the wrapper looks like in R. So again, we are using a macro defined by the R API to essentially cast the expression passed by the user as a array of floating point numbers, and we're also grabbing the length. Here we're actually calling our tally function, and here we're allocating the return value and then unprotecting it to make the R memory allocator happy, and then returning it to the caller. Again, method table and registration routines looks a lot like the Python one. So I guess you can't copy and paste your way to success, but it is not all that different. And I guess some miscellaneous stuff, writing cross-language tools, dependencies, there's a few things you have to worry about. Dependencies obviously don't depend on APIs from the host language. For example, NumPy or RMath when you're writing a tool to be called. So if you're writing a tool that you want to expose to R, don't use NumPy. When you're writing a tool that initially targets R and you want to use it in Python, don't use some of the R random number generators, obviously, except that makes installation a little bit more difficult for your users. If they're Python users, they would have to install the R math library, and then conversely for Python users. So also dealing with errors is a little tricky when you're crossing a language boundary. Generally, it's probably best just to use error codes to signal problems. Obviously, definitely don't call abort or exit. These will quit the process running the host language. And in general, most users expect exceptions rather than the process dying. Memory allocation is also tricky when you cross language boundaries, especially among garbage collected languages. It's always tricky to decide who should actually own and deallocate that data. So if at all possible, do your allocation and deallocation in the host language, and then have the host language just pass around pointers. And then also logging and verbosity. It's probably best to make it optional rather than just printing to standard out. This often doesn't end up in the place you expect, especially in R. It tends to actually not get shown or turn up in odd places or out of sequence. Also, trust the compiler. It's much, much smarter than the rest of us. Your goal in any compiled code should get it to compile without warnings. Warnings today are probably going to be errors in the future. The compiler chooses to warn for very specific reasons. I guess the ones I encounter most often are undefined behavior, also unused variables too. And finally, I guess some parting thoughts. Meet users where they are, reach a larger audience, and make a bigger impact. So with that, I'll take some questions. The code examples are up on GitHub, and then I'm on Twitter, and that's my name.
All right. Does this work?
Oh.
So, yeah. So I've actually done this before. I was wondering why you guys didn't use Swig, which would auto-generate everything.
We've used Swig, not extensively because nobody really, it's just not a tool that's in our tool belt. And it actually, kind of like Python too, it generates a lot of code. And it generates code that's sometimes hard to read and hard to reason about, especially when you run into compilation errors and things like that. But yeah, I guess I probably should have put Swig on that slide as probably another very, very common route to doing the same thing.
Any more questions?
Just curious why you didn't go the shared library route.
Well, I guess this is the tally function itself would be in a shared module, and then I guess the C code itself is a shared module, but the Python module is calling that in turn. So we're using the Python C API to define a Python module itself. So the R side is also the same. So you would compile your library into a shared module or shared object, and then then it just gets loaded at runtime and the symbol's located. And that's what the method table is for, is telling the interpreter where to find those things in the shared library.
Any more questions or comments? No? I actually had a quick question, since we have time. What's your experience in kind of crossing the border between higher languages, so Python to R and R to Python? I think as a non-programmer, there's just things that are in R that are very nice, and I would like to do everything from Python. So
yeah, I guess
they might be running very fast because it's C under the hood, but it's all code in R. So in terms of developers' time, the fastest is just code it in R.
Yeah, the fastest is to work in the language you're comfortable in. So as a tool builder, I want to make sure that the tools that I write are usable to a larger audience, so that they don't have to make that choice. They can work in the language that they're comfortable with. So if your workflow is already in Python, stay in Python, right? It would be fantastic if that one crucial tool that's written in R was also available in Python.
So just a quick question about your workflow. Can you give some
Sure.
examples of how this fits into the different teams that are working in your organization? So you mentioned that you were a tool builder. So how are you building these tools so that they're available to the people working in their respective languages?
So yeah, I guess I neglected that part of the background. Civis is I guess at first a people sciences company. So we do a lot of consulting work where a person is the unit of analysis. So predicting who will support a nonprofit, who will turn out to vote, who will drop out of school, things of that nature. So a large portion of the company do client-facing work, solving these types of problems. And I'm on an R&D group where we interact with them and try to find what are the commonalities among the things that they're solving and turn those into tools so that the next time they do it, they don't have to do it from scratch. Ideally, there's a push-button route, but that itself turns out to be very difficult. So most of the people doing client-facing work come from multiple disciplines. Like I said, we have a lot of physicists, some economists, a lot of people from various social sciences, political science. And depending on where they come from, they're very comfortable working in R, or they're very comfortable working in Python. And depending on, we have some path dependence on when particular parts of our workflows were developed. So we have some part of our tool base built in Python, some part built in R, depending on who actually started the project. So completing a task from client data to model or slide deck or whatever the output is usually involves chaining together a whole bunch of discrete packages and tools. And there may be some Python, there may be some Go, there may be some R. And the most robust thing we found so far is to just write all the data to a file and then pass that to the next job. But that's definitely not the ideal. And then we also have this notion of some things you do in batch, some things you do interactively. So before you know the solution to a problem, you're doing interactive data analysis. You're doing some plots, you're doing some aggregations, writing SQL queries, things like that. At some point, you solve the problem, and then you need to solve that same problem again. So then you want to turn it into a batch type solution, and we found that R doesn't necessarily fit that type of work. Python does. So we try to push people toward developing batch type tasks in Python rather than R, but they still like doing their interactive work in R. And you may use the same algorithms in both places, and reproducibility is also very important to us. So being able to do the same analysis in both languages is kind of our gold standard. I don't know if that long-winded answer, if that answers your question.
Any more questions or comments? No? All right, well then join me in thanking him again.